We are on SIP-8 today as part of our SIP reading club, which had a little bit of a hiatus at the end of summer, but I'm happy to have it back up again and rolling. This week we have Pavitthra, Distributed Systems Engineer at Hiro, Reed, Software Engineer at Hiro, and Aaron, Staff Scientist and Engineer at Hiro. Let's get this going. Reed, Pavi, take it away.
Awesome, thanks, Shannon. So yeah, today we're talking about SIP-8. This is kind of the last of kind of the original, this is like the last SIP I think that we intended to talk about, and then SIP-9 was added, while we were doing this reading club. So I think at some point we'd like to do a reading club on SIP-9. But anyway, SIP-8 is about clarity parsing and analysis cost assessment. So not too far off from some of the things that we talked about when we were discussing SIP-6. So yeah, maybe we could start off. Aaron, could you tell us a little bit about, so clarity is not, it's not a compiled language, right? So, but there still is a cost to assessing and parsing the code into an AST. Could you maybe tell us a little bit about what is actually involved in parsing clarity and like what actually happens that incurs cost?
Yeah, sure. So I guess there's kind of two things going on with a contract before a smart contract ever gets executed by the stacks node. The first thing that happens is parsing the contract into an abstract syntax tree, which we call an AST. So the idea here is that nodes in the Clarity VM they see a string essentially from a transaction that has all of the text content of the smart contract, and they need to translate that into something that the Clarity VM can operate on, that machines can operate on, and that thing is what we call an abstract syntax tree. It's basically a translation from text into this internal representation of function calls, arguments, variables, literals, things like that. So the reason that you need to assess a cost here is that before you can begin executing the Clarity contract and assessing runtime costs associated with it, you need to do this translation step. And so anybody that publishes a contract needs to pay some fee, because you could imagine that they give you a really, really big contract to parse, and the VM or stacks nodes are going through the text, scanning it over, pulling out all of the number literals, all of the variable names, all of the bindings, all that stuff, and it exhausts their CPU capacity, and the network becomes overwhelmed. So we don't want to do that. We want to assess a cost for these operations. So that's parsing. The second thing that you want to assess a cost for before execution is the static analysis that the Clarity VM does before it ever executes a contract. There are a bunch of different analyses that the Clarity VM does, but one of them is, the major one is a check for type coherence. So basically all the Clarity code that you write before the Clarity VM even tries to execute it, it wants to make sure that the arguments that you supply to functions are the correct type, that there's no unbounded sizes for any of the variables or arguments. Everything has a sort of well-defined type and maximum size, things like that. And that all happens before you start incurring runtime costs. So that's the second kind of thing that we need to be sure to assess costs for.
So, in SIP-8, it kind of discusses, briefly touches on on like the different passes that the AST goes through. So there's type checking, there's also other types of work, such as like read-only checking, trait checking. Could you like maybe like briefly describe the different passes the AST goes through?
Yeah, sure. So the first pass that the AST will go through is the type checker. The type checker, basically, it does a couple of different things. So one of the first things it does is it makes sure that any Clarity contract, when it's published, if it's doing contract calls to other contracts, that those other contracts exist at the time of publishing. This is done to make sure that the Clarity VM and the subsequent analyses all have some sort of like ground truth that they can look up. Like if they're trying to figure out, say, what the return type is for a contract call, you need to actually know the contract being called before you can figure out the return type. So the type checker does that kind of work first. And then it starts ensuring that, types are all sort of being legally used. So that's things like you can't add two lists together because like that's like a nonsensical operation. So it checks to make sure that when you're adding two integers together, or if you're operating on unsigned integers, that you do a conversion before you start combining them with signed integers. Things of that nature. Probably the most sophisticated part of the type system is the size checkers. So one of the things that the type checker does is like when you have like a data map or a stored data variable, you like specify the maximum size that can go into that variable. So like you might say have a data variable that's like max list length 10. And it performs a check in the type checker to actually ensure that during runtime, you're doing enough checks to guarantee that, no list over size 10 ever gets stored there. So that's the kind of stuff that the type checker is doing. The next major pass is the read-only checker. This read-only checker ensures that if you have a function that's like define read-only, so the contract specifies that it's a read-only function, that it's actually read-only, like it doesn't have any operations within it that like mutate any data, transfer any tokens, things like that. That's what the read-only checker does. And then the other pass that we have is the trait checker. The trait checker is just responsible for checking whether or not if you specify that your contract implements a given trait, the trait checker ensures that that trait exists and that the contract actually implements all of the functions and has the correct return types for that trait.
So I actually have a follow-up question to this one. And so basically early in the SIP, there's like a line that says costs for static analysis are assessed during the type check pass. The read-only and trait checking passes perform work which is strictly less than the work performed during type checking, and therefore the cost assessment can safely fold any costs that would be incurred during those passes into the type checking pass. So I understand what that's saying, but as evidenced by like our recent benchmarking work where we're trying to basically get exact constants for like our clarity function and things like that, I wonder why the decision was made that like we could fold those costs in, because like I know in general we do care about constants and like figuring those things out.
Yeah, sure. So there's basically there's kind of two sort of motivating reasons here. So one is that a sort of low-hanging fruit optimization on these multiple passes is to try to do them, like to actually fold them into a single pass or like a single visitor. So like the major thing that's happening in all of these AST passes is that we're doing sort of a simple descent down the AST. And then every time we get to a node that references a different smart contract, we have to do a data fetch. Those are sort of the most costly things going on, is the AST descent and then the dereferencing of other smart contracts. The thing about all of our analyses is that all of them are descending the AST basically in the same way. And then also nodes that reference other contracts always reference those same other contracts. And so there's like an opportunity to maybe like factor things around and optimize that. And we would want the cost assessment framework to sort of fit that model. The second reason to do this is that it makes cost prediction of the parsing and analysis passes much more straightforward. Because if every pass is just getting folded into the type checker pass, and you have like an estimator that basically just looks at the runtime given an AST size, which is, it should be something like linear with the number of AST nodes, and then some sort of additional linear component that depends on the number of like referential AST nodes. And if you're trying to do that estimation, it's like a much easier job if you only have to do that estimation with one pass.
Aaron, I was thinking maybe we could talk a little bit about the dependency cycle detection pass and just go into some depth about the algorithm that's used there.
Sure. So, so the dependency cycle pass is basically used to discover the order in which the other analysis passes should be going in to look up sort of internal references. So the idea is like if you define a public function somewhere, it's actually like sort of perfectly legal clarity to use that function in a function that's defined like higher up in the file. But if you do the analysis, you descend through your analysis in the order that the file is written in, and the type checker is going to get like caught and say like, hey, wait a second, I've never seen this function name, you've got an error. So we wanted to avoid that case. And so what the dependency cycle checker is doing is first it's ordering the functions so that, there is a way to go through the AST in an order such that, you don't have these kinds of errors. And then the second thing it does is like if there's actually a dependency cycle, so like you have like a function A that uses function B, and then function B is defined that uses function A, those cycles sort of error early so that you're not like trying to do further analysis and like discovering that error later on. The way that the dependency cycle checker works is, it basically does a descent of the AST. It associates each AST sort of top level element with like a list of dependencies. And then it tries to do a search through those dependencies until it encounters a repetition. So like it has like a seen before list, then it descends. If it encounters something that it's seen before, then it detects a dependency or a circular dependency and it exits. The runtime of this is like think n log n in the number of dependencies, which you can approximate as, I think, just the number of AST nodes, because you can't ever have more dependencies than AST nodes. That's my best recollection from memory. So if I'm wrong, I apologize.
Got it. Thanks. Avi, did you want to follow that up with another question, or should we maybe, I don't know, there's not that much left to discuss about SIP-008. It's kind of a shorter SIP, and so we were talking a little bit before we went live about talking about some tangential stuff that's been going on, discussions that have been going on recently regarding like fee estimation and block limit stuff. What do you think, Pavi? Should we keep going on SIP-008 for a little bit?
I would agree. Like, I think we should switch over. But I think before we switch over, if anyone from the audience has any questions about SIP-008, like, we could discuss those now. So yeah, feel free to raise your hand. Okay, yeah, no one seems like they have any specific questions. But yeah, anyway, anytime if you have a question about SIP-008, like, feel free to raise your hand. But I think we can move on to the fee estimation stuff. I think it's pretty topical, and there's been a lot of discussion about it in the Stacks core dev, and there's like a discussion post as well in our repository. So yeah, Reed, you want to start with a question?
Yeah, sure. Well, I guess just to get everybody up to speed. So maybe we could, maybe a good starting question would be, Aaron, could you tell us a little bit about, how does fee estimation currently work? What's kind of the optimal scenario for fee estimation? And this proposal is kind of, a step in the middle. So maybe you could talk about why we can't just go from where we are today to kind of the optimal case right away.
Yeah, sure. So I guess to start with, I'll describe what we have today, or what we have in basically an outstanding PR is miners are basically looking at their mempool. There's a ton of different algorithms that miners could choose to use to pull transactions out of the mempool, evaluate whether or not they can be included in the current block, and then include them in the current block. If miners are sort of behaving rationally, the thing that you would expect them to try to do is try to pack as many transactions as they could possibly pack into a block, such that they get the maximum transaction fees from the transactions that they've packed in. This is a sort of non-trivial problem in general, because we have these 5-dimensional execution costs. There's block limit that varies in those dimensions, and so it's kind of hard to do in a perfect world, and then it's really hard to do if you don't have a good way of estimating before you execute a function how much of the block limit is going to be consumed, right? So if you think about what a miner is doing when they're evaluating blocks, they're pulling transactions out of the mempool, they try to execute it, and then only afterwards do they actually know the exact execution cost of that transaction. So if they're trying to figure out how many transactions they can include, which ones they should include, which transactions are paying a higher fee compared to how much execution cost they're consuming, it would be really hard work, literally expensive, costing CPU cycles, time, all of those things, for the miner to be doing this speculatively, where they only have the vaguest of guesses about how much a transaction costs to execute before trying to include it in a block. But anyways, the situation that miners, the mempool, transaction submitters are all in today is that the default algorithm for including transactions in a block basically just ranks transactions by the origin nonce. So it doesn't even incorporate any sort of reasoning about fees. We have an open PR, or Jude has an open PR that does look at the raw fee. But basically all it does is look at the raw fee number and then try to include the transactions with the highest fees. The problem with that is that you might have like a very expensive to execute transaction, like a contract call that does like a ton of work, that's paying a fee that's only sort of slightly higher than like a stacks transfer transaction, which is much cheaper to execute. And so the miner is suffering because they don't have a way to estimate the fee rate of each transaction. And so the proposal that I outlined if you look at the Stacks blockchain repo and go to discussions, there's like a proposal for enhancing fee estimation. This proposal tries to like sort of piecemeal introduce mechanisms into the ecosystem that would allow us to have like better ability, have miners have better ability to estimate fee rates, but also users that are submitting transactions have some better ability to pick a fee so that they get included in a block. So that was a big rambly answer, and I think I maybe only answered one of your questions about it.
Well, maybe we can talk about the proposal before talking about kind of more future-facing stuff, because there was I think a lot to unpack there.
Yeah,
I think it'd be interesting. Oh, sorry, Reed, go ahead.
No, go ahead, Pavi.
Okay. Anyway, I think it would be interesting to like maybe go through each part of the proposal part by part. Because there's like 4 distinct parts that kind of like all are separate, but a little bit chronologically linked in how they need to be implemented. But anyways, so the first part was the code blind estimator, where we would try and create a system where we could take a transaction and provide some kind of estimation for how long that transaction would take. Anyway, like I have some questions on it, but like before I ask, Aaron, do you want to like quickly describe like what we're trying to do with that?
Yeah, sure. So the idea with this cost estimator is that basically like what a miner or mining algorithm wants to do is like pull a transaction out of their mempool, sort of take a cursory look at the transaction, like look at, what contract it's calling, maybe the arguments to the contract function that it's calling. And then based on that sort of like cursory look, be able to come up with a relatively accurate estimate of how expensive or how much of the block limit will be consumed if they include that transaction in the block. You can imagine that these estimates, like a miner might want to err on the side of being pessimistic. So maybe they like overestimate all these transactions for how much they cost, things like that. But anyways, so if the question you're trying to answer is like, how much do I think this transaction is going to cost? The cost estimator is like supposed to basically fulfill that need for miners. There's a ton of different ways that a cost estimator could be implemented. One of the cool things about Clarity is the fact that because it's not a Turing complete language, you can actually do static analysis to determine upper bounds on these things, and you could like store that static analysis and like recover it as a miner to try and figure out how much a transaction would cost. but there's also simpler approaches. And in this proposal, I basically say, like, we should start with a simple implementation, and then other people can refine it from there.
Yeah, anyway, so I had some questions on like maybe your preliminary thoughts on how we're actually going to do it. So given that it's like code blind, right? For the most part, it's like, I guess, argument blind as well. Other than like the case that you mentioned in the proposal where like if an argument is a list, maybe we would want to consider the list size in calculating the final cost. But in general, are we trying to basically have a system where we're always taking the worst case? Or are we trying to do an average? Like, yeah, I guess what's the approach we're going to take?
Yeah, so I guess like the way that I would think about it is like probably the first implementation would be like a naive and pessimistic estimator where, the estimator basically receives the actual execution cost for a given contract call. And then it just like builds up by either like a windowing system or like, some sort of average weighted towards, the highest outcomes. Yeah, you could imagine like a system where, you have like a 10 window or a 10 slot window, and you take the average over that window and you only eject things out of the window for new measurements if the new measurement is greater than the minimum that you've seen so far in that window. And that would be like incredibly pessimistic. You would basically always judge a transaction by its worst case. That's probably a sort of first pass at building one of these estimators. But I think that the ultimate goal with the framework would be that building these estimators is kind of independent enough work that, if you're a miner or, you're contracting with a miner or whatever, and you think that you could get more value out of a more accurate estimator, then you would build an alternative estimator, and it would just be sort of plug and play in your miner.
Cool. So would you imagine just like wondering, for this like very preliminary cost estimator that we're creating, would we take into account any sizing of like lists or any variance in the argument?
I think that the question is ultimately, I think, like kind of an empirical one. Like if the error percentage on observed transactions is pretty low, then maybe you don't even need to consider the size of the arguments at first. I've done some analysis of transactions so far in mainnet, and really without even taking into account argument size, you can make a pretty good estimator. The one area where that's not really the case is in estimating the cost of contract publishes. So a contract publish, like the larger the contract, like the more expensive it's going to be, and contracts can be like really different in size. And so a sort of naive, pessimistic estimator really, really overestimates for a lot of contracts. So, yeah.
Awesome. Cool. Yeah, Reed, do you have any questions on this like section of the proposal, or we could move on to like the second part, which has to do with block assembly?
Yeah, I'm cool with moving on. So yeah, maybe, you mentioned in this proposal that the cost estimator, or the results of the cost estimator, will mainly be utilized by the parts of the code base that deal with block assembly and block validation. So maybe starting with block assembly, could you talk a little bit about how the process of assembling a block will take into consideration these estimates and how that will happen?
Yeah, sure. So right now, the sort of default algorithm for block assembly, which I described before, doesn't do any consideration of a transaction's execution cost. And so once you have an estimator that can provide you with this execution cost struct or estimate, the way that the miner sort of traverses the mempool and orders transactions for inclusions in the block would need to change to incorporate this new information. There's probably a ton of different approaches that a miner could take, even given the execution cost. Because again, like the execution cost is this like 5-dimensional thing. And so, if a miner wanted to be like really aggressive about packing their block, they could do this thing where they just look at every transaction in the mempool, they figure out an estimate for every single one of those transactions' execution costs, and then they try to solve a 5-dimensional integer knapsack problem, which I think is like NP hard, but there's like good heuristics for. And then they could like create the perfect block that rewards them all of their fees. I suspect that that's not going to be a good strategy to go down for miners, but like if somebody wants to build that, go for it. I think that the first sort of strategy that you would want to come up with is translating this execution cost into some kind of scalar value that gives you kind of a heuristic solution to this block fill problem. Once you've translated the execution cost into a scalar, you look at every transaction's fee, and you just like divide the fee by the scalar, and that gives you like an estimated fee rate. And then you basically just want to order transactions by fee rate descending and stuff them in the block that way. But I think like the cost estimator, the idea here is that we want to do something sort of simple that maybe improves upon the current default algorithm, but like exposes enough of a interface that people can plug in other approaches as well.
Got it. So Aaron, when you're talking about converting the cost estimate into a scalar value, is what you mean by that taking, like, because the cost estimate ultimately is like a struct that has 5 different values? Do you mean kind of finding a way to represent that with a single number just to make ordering easier?
Yeah, exactly.
Okay. Got it.
Yeah, in the proposal, Aaron basically just was taking the volume of that, like in the 5-dimensional space. Yeah. Anyway, so the next component that this proposal discusses is updating the fee rate endpoint. I guess what we could talk about is what's there today and what we want in the future.
Yeah, sure. So the fee rate estimation endpoint is kind of like the other half of this problem. So from the perspective of the miner, if you have a cost estimator and you have the ability to assemble blocks using cost estimates, the problem is kind of solved for you. Like, you know how to build a block. But for other participants in the network, they're still kind of blind about how to get their transactions more included or included faster in blocks, right? So as a user, whatever, developer or library author, like, I want to have the ability to build a transaction, make some query to the network that's like, hey, what fee do I need to be paying for this transaction? And then decide whether or not it's worthwhile or whether or not I want to increase the fee, whatever, to get included faster, all those kinds of things. So the fee estimation endpoint that Stacks nodes have today just reports the absolute minimum fee for relaying the transaction in the network. So that's like, if you pay lower than this fee, like a Stacks node won't even accept it into the mempool. So that doesn't really tell you enough information to get your transaction included more quickly. And so the idea with this component is like adding a better endpoint and then also a little bit more calculation on the Stacks node side to sort of predict a good fee to use. And this is like sort of like slightly a different problem than the problem that miners are trying to solve when they're building blocks. So a fee estimation endpoint needs to look at a couple things. So it looks at blocks that have already been built. And it says, okay, what were the fee rates that were getting included in that block? And to do this, you need to have sort of your own idea about what a fee rate is, right? Like you have the same challenge of like translating execution costs into a scalar, figuring out what the paid fee was, and then turning that into a rate. So you can look at assembled blocks and figure that out, but you can also look at the current mempool and see what the estimated fees all of these transactions in the mempool are paying, because that's like who you're competing against when you're submitting a transaction. So those are like two different approaches, and then there's like within those two different approaches, there's like a ton of different other sort of strategy decisions that you need to make. Like, you need to pick a scalar, you need to pick, like a prediction about like what other transactions might enter the mempool, all sorts of stuff like that. So again, like I think that this is something that you would want to be pluggable, but we would probably come up with a sort of simple default that basically just looks at, the median 95th percentile, 5th percentile values of the most recent blocks, and use those as a fee rate estimate, and probably the same approach, the sort of like same default scalar representation of execution costs that the default miner uses.
Cool. Yeah, I don't have any further questions there. Yeah, so I guess we can move on to the last part that you proposed, which is changes to mempool admission. Can you describe like what you're intending with that?
Yeah, sure. So this is kind of like the least fleshed out part, because it's kind of got the least impact, and it's also simultaneously the most dangerous change that the network could try to introduce. So the idea here is that like right now we have this like minimum relay fee in the Stacks node, where the Stacks node just like rejects your transaction, like it won't accept it into its mempool, and it won't propagate it to other nodes in the network if you haven't paid over this relay fee. The relay fee is basically just paying for the cost of sending bytes. Like it's not paying for the cost of considering the transaction. So if I had a really expensive contract call, the minimum relay fee would have like almost nothing to do with the amount of work that miners have to do to consider the transaction. And so the idea is that like if nodes have like a very good estimate of what a fee should be for a given transaction, they could reject it from the mempool if it doesn't pay like, within 4 standard deviations or something of what it estimates that transaction should be valued at. And this would just like help, alert alert you that like, this transaction you're about to submit is probably never going to be included in a block if you submit it. So maybe you should think again about what sort of fee you want to pay. And it also like helps alleviate some congestion in mempool syncing. But it has a potential negative outcome where, if some stacks nodes have upgraded or have a particularly advanced estimator and other stacks nodes don't, then you could be in a situation where like there's some stacks nodes that are willing to accept your transaction into the mempool, but they're not able to broadcast it to other nodes. And then you'd be in a situation where you're like, well, I think that my transaction was accepted by a stacks node, but like I can't see it elsewhere on the network. Like I can't see it on different explorers. It's never getting mined. What's going on? And that could be like a really annoying situation to be in, which is why I think mempool admission changes really need to be thought of as sort of the last thing to be improved on.
Cool. Reed, do you have any questions?
I don't think so. I mean, we're almost through kind of all of the topics outlined in the proposal. I guess we could talk a little bit about like how you would actually test these changes, and like yeah, I guess like a question I had that I wasn't super sure about reading through like this testing section was like can we test this stuff on like any of the kind of historical data that we have that's been kind of written into the chain, or do we not have enough, just given that like we don't have a history of kind of the states of the mempool at various times and whatnot to really effectively do that? And then maybe also, Aaron, you could just talk a little bit about the testing mechanisms that you have outlined in this proposal.
Yeah, sure. So I think that there's certainly a ton of components here that can be tested, both in terms of like just like standard unit tests where you're like, I think that, this piece of code should do this thing, and have those assertions. Like, can write unit tests for a lot of this. The second level of testing is that like things like the code the cost estimator, those you can really use historic data from mainnet or testnet, and look at how predictive or how good the estimator is, and you could just like look at the squared errors of the estimates it's making, or have some other metric that you're trying to optimize for, and figure out like how good of an estimation it's doing. Block assembly can be like a little bit harder to test, just because you're right, we don't have easy way to get like historic data about like how a mempool has evolved over time, especially because like the way that the mempool evolves is like impacted by the transaction selection algorithm. Like there's a lot of like weird interplay going on there. That doesn't mean it can't be tested. I think that like block assembly is actually somewhere where unit testing or integration testing can actually be pretty good. The other thing that can be done is you can run a mock miner and compare the mock miner's assembled blocks against the sort of actual blocks and see that it's doing a better job optimizing for fees, because it's building blocks that would like have a higher fee. So those are the, I think, sort of two ways that everything here can be tested. I think that, like, yeah, most things, unit tests can be useful. I think pretty much everything but the assembly, the actual final assembly. So, yeah.
Cool. Are there any questions from the audience? I think Reed and I might be wrapping up.
Yeah, I don't think I have any more questions.
Cool. If anyone does have any questions that come to mind later on, you can post them in the stage chat or community general and just tag us. We'll be happy to answer there. Just one final check. Anyone? Pavi, Reed, all good?
Yeah. But yeah, if anyone has questions, like we can still go back to SIP-008, questions on that. So.
Yeah.
All right.
I just had a clarification. Oh, sorry.
Go ahead, Pavi.
Yeah, I just had a clarification question on something Aaron said, but might not appeal to everyone. Just following up on something that I didn't understand. So earlier when we were discussing SIP-008, I asked you about like folding in the costs of the read-only checker and the trait checker into the type checker, and you said that you could figure out the runtime based on the size of the AST, and that would be linear. Could you like expand on that? I didn't fully understand that.
Oh yeah. So basically, the idea with all the analysis passes as currently implemented is that the way that they work is they do a single pass over the AST, and so if you're trying to estimate the total amount of work done during, like, say, type checking, that as the AST grows, like as you add more elements that the type checker needs to pass over, you're going to incur more cost. It's definitely true that there's like some things that would be more expensive to evaluate than others, but for the most part, they all have like a very similar cost, like as you're sort of descending this tree, and they also have pretty similar run times. The problem that you'll get into is when you hit nodes that refer to other contracts. So like, let's say you hit a contract call node. At that point, you need to load in another contract to continue performing type checking, or you need to like fetch data associated with that contract. And so you can estimate, the cost of doing, the total cost of doing the analysis with a linear method that maybe has pulled out those references. So it's like linear in the size of your contract, and then maybe also counting the number of references to other contracts.
Got it. All right, cool. Okay. Yeah, well, that's all I have. So I think that pretty much ends all of the questions.
Cool. Thanks, Hiro team. Our next session on SIP-9 is going to take place on September 15th at 2 p.m. And that will have Aaron and Frieger joining us. I see Frieger in the audience. Looking forward to that. This session is going to be posted to the Stacks YouTube channel, say in the next day, I would say. But otherwise, thanks for joining us. Enjoy the rest of your week.